Arduino focuses on ease of use for non-programmers. That introduces a lot of problems around performance, functionality and flexibility. There are also reliability issues to consider. If you are beyond the beginner stage, you will be running into those limitations. Like the proverbial frog in a pan of hot water, you may be missing the signs it's time to move on. I'll show you a few things I've found that I think will hold you back. I want to look at the Arduino core first. That's the layer that sits on top of your microcontroller's hardware. It sets up background tasks like timers and provides easy-to-use functions for I/O. One of the kingpins is digital write. It makes I/O operations easy by hiding the complexity of port manipulation. Despite the central role it plays, it fails badly on both performance and resource use. But there's no good reason for that. It's possible to have ease of use, speed and efficiency all at the same time. I'll demonstrate that with a real-world example. These NeoPixels use a simple protocol. It should be possible to implement that with digital write. But because it's so slow, it can't manage the 800 kilobits per second they use. However, a properly engineered version handles it with ease. Before we look at that, let's just see how bad the original is. This sketch generates 2 pulses on an I/O pin and repeats them at regular intervals. Notice how much code even a simple task like this produces, and the oscilloscope shows us how slow it is. At 2 microseconds per box, we have 11 microseconds repeat rate. NeoPixels require 4 and 800 nanosecond pulses. Digital write as it stands isn't even close. This fast I/O library replaces the existing routines. We end up with a lot less code and a lot more speed. With 5 boxes at 50 nanoseconds per box, it's 250 nanoseconds repeat rate, more than 40 times faster. Fast enough even for NeoPixels. But we can have more functionality and even more speed. The library comes with some additional routines. One is digital pulse. No prizes for guessing what it does. Let's try it out. 2.5 boxes between pulses and double the speed again. We've reached the maximum speed possible, 1 clock cycle per I/O operation. And that's all achieved without resorting to port manipulation. A look at the source code for the original reveals one of the things that's going wrong. This lump of code gets to run with every I/O operation. It automatically switches pins back from PWM mode. I can't imagine who would set up a PWM pin then use it with standard I/O commands. But they're saved the trouble of swapping back manually if they do. Unfortunately, everybody gets a massive performance hit as a result. That's a terrible trade-off. Ease of use pushed way beyond what's necessary. One of the reasons often cited for using Arduino is it comes with a vast collection of easy-to-use libraries. But like the core, they don't match up to expectations. A major spoke in the wheel is the programming philosophy and standards adopted. They're clearly stated on the Arduino website and demonstrated in the infamous blink sketch. It uses the delay function. When that's called, it blocks everything else from happening. It might be easy to explain to beginners, but it's no use for real-world applications. Unfortunately, Arduino wants library writers to follow that example. They encourage them to put most of the functionality into an all-encompassing blob. The goal is ease of use, but like delay, the results are often clunky, inflexible and uncooperative. Let's look at a simple situation where that approach doesn't work. Here is a one-wire temperature sensor. It's popular, so there's an Arduino library for it with instructions and code examples. Very easy to implement, and the output appears on the serial monitor. And here is a 7-segment LED display. It's got a library with instructions and examples too. We can try and combine the two to make a standalone thermometer. The sensor example sketch is a good base, but the original is verbose. There, that's better. We can link the two together, connecting the sensor output to the display input. Oh dear, that's not good, but just what we'd expect. The problem is the sensor library follows the Arduino programming paradigm. Those devices can take nearly a second to come up with a result. The sensor routine starts the conversion and waits for it to complete. There's no processing needed, the sensor is doing all the work unaided. but the routine still sits there, needlessly blocking all other processes. The LED library is left hanging, unable to refresh the digits. But with the merest sprinkling of sophistication, we can get a much better result. This library is one for the same device but taken from a different platform with a more reasonable approach. As a result, it has much less impact on other tasks. All that's required is to start the conversion, then occasionally check progress. When the result is ready, it can be quickly processed. The LED display gets continuously refreshed without any disruption. Like the core, we get lots of pain for little gain. A tiny improvement in ease of use for one area has a drastic effect on performance in many others. Let's take a look at an Arduino schematic next. Question: how often do you see 100 nanofarad capacitors connecting two digital signals? There are good reasons why the answer should be never. That's why this one sticks out like a sore thumb. It connects the DTR output to the reset input of the 328P. That's supposed to generate an automatic reset at the start of programming to trigger the bootloader. DTR is active flow and asserted for the duration of programming, so it can't be used directly. Instead, it's passed through that capacitor, turning its falling edge into a negative going pulse. Sounds like a good idea, except it's not. That arrangement cannot produce a reliable reset. Let's look at a typical case of VCC at 5 volts. The datasheet tells us the reset pin needs to get down to 0.5 volts or below for a reliable reset. Therefore, the pulse needs to have a magnitude of at least 4.5 volts. For this arrangement, the guaranteed minimum magnitude is VOH min minus VOL max. From the datasheet, that's 4.1 minus 0.8 or 3.3 volts. 1.2 volts short of what is required. And if the programmer and target have different VCCs, the difference between them also needs to be considered. If you want a better understanding, I recommend this MIT Open courseware video. See the link below. In most cases, VOH is going to be a bit higher than 4.1 volts and VOL is going to be a bit lower than 0.8, and the reset will occur a little bit above 0.5 volts, but 1.2 volts is digging deep into the reliability margin. But there's worse. The same capacitor produces a nasty spike right at the end of programming. Just like the falling edge of DTR gives a negative going pulse, its rising edge gives a positive one. That nasty spike is on your reset pin and will very likely bump your device into high voltage programming mode, with the possibility of bricking it. A diode was added to Rev 3 of the Uno, presumably to catch that spike, but I've not seen that fix on any other board, so I guess the problem is still there for them. Not only that, the spike goes straight out of your Arduino on the various reset pins. Whatever you have connected will get a nice dose of the same thing. If you've been having trouble uploading to your Arduino or found it bricked, then there's a good chance this capacitor is the culprit. Arduino uses a bootloader as the main way to upload code to the target. Most of the advantages of that method vanished when serial ports disappeared from PCs. Now it requires a virtual COM port. Arduinos usually emulate one with a USB-based microcontroller. Unfortunately, all they loaded into it was a standard USB to serial application. The minimum they should have done was to upgrade it to generate a proper reset signal rather than DTR. The dodgy capacitor we've just looked at wouldn't be necessary. We'd be getting a reliable reset pulse with no nasty spikes. They could have taken it even further. Let's see how by comparing an Uno and an Atmel Explained Mini. Both have a virtual COM port, so we can still use a serial terminal if we want to, but Atmel included an ISP or in-system programmer in their offering. Like the Uno, we can write to the program memory, but now we can also read and verify it. And the same goes for EEPROM. What ISP gives us that the bootloader can't is full access to the microcontroller. We can set its configuration fuses, the calibration values, and even the security bits if we want. But there's more. They've also managed to squeeze a debugger in there. That means we can set breakpoints, single-step our application, examine and alter memory locations, and examine and change registers. A much more effective way to debug code than serial prints and flashing LEDs. The Atmel board also uses the upgraded BP version of the processor, so there's extra I/O pins, extra serial, extra SPI, and extra I2C channels, and 4 more PWM outputs. Yet we pay twice as much for an Uno as we do for the Explained Mini. I'll stop there. However, I think I've demonstrated that beneath the shiny surface, Arduino is slow, bloated and clunky. And I think I've shown that's mostly down to the single-minded focus on non-programmers. But there's something more insidious going on. Because most of the complexity is hidden, you're losing out on vital opportunities to learn. That won't matter much to casual users, but if you want to get the most out of microcontrollers, then Arduino isn't a good long-term choice. Anyway, I hope you found the video useful and informative. Please like and subscribe and all that nonsense, and thanks for watching.